Determine all intervals of increasing trend or decreasing trend and determine the coordinates of all maxima, minima, plateaus, or cliffs for the function f of x equals 2x plus 2 divided by x squared plus 3. The first thing to do is find the domain. F of x equals 2x plus 2 divided by x squared plus 3 has a denominator. And for the domain, the denominator cannot equal 0, so x squared plus 3 does not equal to 0. We can solve for x by subtracting 3 from both sides, so x squared cannot equal to negative 3. We can take the square root of both sides. The square root of x squared cannot equal to, on the right side we will end up with plus or minus due to the square root of negative 3. Square root of x squared is x, and that cannot equal to plus or minus, and the square root of a negative number is not a real number. So x cannot equal something that isn't a real number anyway, and the domain is only real numbers, so the domain is all reals and there's no real numbers that x cannot be. They're just not real. The domain will stay as all real numbers, or negative infinity to positive infinity. The next thing to do is find all critical numbers. We will take the first derivative. F of x is a quotient of two expressions here, so the derivative f prime of x will require the quotient rule, which will be the derivative of the numerator times the denominator left alone, minus the numerator left alone, times the derivative of the denominator, and the entire thing over the denominator squared. We can distribute the 2 here in the numerator. That will give 2x squared plus 6. We can distribute the negative and the 2x in here, which will give a negative 4x squared and a negative 4x. Over the denominator left alone. It's quantity squared, it's technically factored. In the numerator, we can combine together like terms. There's a 2x squared and a negative 4x squared. That will be a negative 2x squared. We can write this in descending order by putting the negative 4x next and then the positive 6. Over that same denominator. We want to fully factor the first derivative. There is a common factor of 2 in the numerator. We will also bring a negative out with it since we have a trinomial quadratic. It will make the x squared coefficient become positive. It'll be a positive 1x squared, a positive 2x, and a negative 3. All over the denominator. We want to try to further factor the trinomial quadratic. It can factor into x and x. We need two numbers that multiply to be a negative 3 and add to be a positive 2. It sounds like positive 3 and negative 1 will take care of this. And we can leave the denominator alone. So we have the first derivative as a single fraction. All powers are positive. It's fully factored. We can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. Starting with the numerator, negative 2 times x plus 3 times x minus 1 equals 0. Solving for x, the negative 2 can just divide and doesn't matter here. It'll give x equals negative 3 and x equals 1. Now working with the denominator, x squared plus 3 quantity squared equals 0. We can start by taking the square root of both sides. Square root and the square cancel, leaving just x squared plus 3. And the square root of 0 is 0. We can subtract 3 from both sides. And then we can take the square root of both sides, which will give plus or minus the square root of negative 3, which once again is not a real number. We want to keep only those that are in the domain, so we compare these against the domain, which is all real numbers. Negative 3 and 1 are both real numbers. We keep those. We do not keep the ones that are not a real number, so we can cross those out. We can now draw a domain line, a line representing the domain, which is negative infinity to positive infinity, so it has no left end and no right end. We can put any critical numbers on this domain line in order. Negative 3 comes first since it's less than 1, which breaks the domain interval up into 3 separate intervals. We can pick a test value in each of these intervals. The interval negative infinity to negative 3, we can pick negative 10. The interval negative 3 to 1, we can pick 0. And then the interval 1 to positive infinity, we can pick 10. And we can now test the trend by plugging the test values into the first derivative. We don't care about the value of the first derivative, just whether it is positive or negative. And so the best place to plug in is the fully factored version, which is here. A couple things about this. In the denominator, we have a quantity squared, and therefore that will always be positive. There's no need to plug into that. It will not affect the sign of the first derivative. The negative 2, we will want to be careful to account for that negative on that 2. The x plus 3 and the x minus 1 can be positive or negative, so both of those will matter. So the full numerator will have to be evaluated to determine whether the first derivative is positive or negative. Starting with the negative 10 plugged in there. Negative 10 plus 3 is a negative. Negative 10 minus 1 is a negative. And then times that negative 2, that's 3 negatives multiplying each other. The result is a negative first derivative, which corresponds to a decreasing trend. Plugging in 0 to the part of the derivative that matters. 0 plus 3 is positive. 0 minus 1 is negative. Negative times negative is positive. We have a positive first derivative, which corresponds to an increasing trend. And then plugging 10 in to the part of the first derivative that matters. 10 plus 3 is positive. 10 minus 1 is positive. Negative times positive is negative. We have a negative first derivative, which corresponds to a decreasing trend. So we have a decreasing trend happening from negative infinity to negative 3 union, because it's happening again from 1 to positive infinity. We have an increasing trend that is happening from negative 3 to 1. Right at the critical number of negative 3, we have a trend change from decreasing to increasing. This means that negative 3 will be a relative minimum. It has an x-coordinate of negative 3. It has a y-coordinate that can be found by plugging the negative 3 back into the original function. So y will equal f of negative 3, which will be 2 times negative 3 plus 2 divided by negative 3 squared plus 3. 2 times negative 3 is a negative 6 plus 2. Negative 3 squared is a positive 9 plus 3. Negative 6 plus 2 is a negative 4. And 9 plus 3 is a 12. These can each reduce by 4, so this will become a negative 1/3. And there's the corresponding y-coordinate for the relative minimum. Right at the critical number of 1, we have a trend change from increasing to decreasing that makes 1 be a relative maximum. So we have a relative maximum at an x-coordinate of 1 and a corresponding y-coordinate that can be found by plugging 1 into the original function. So y will equal f of 1, which is going to be 2 times 1 plus 2 divided by 1 squared plus 3. 2 times 1 is 2, plus 2 over 1 squared is 1, plus 3. 2 plus 2 is 4. 1 plus 3 is 4, and 4 over 4 is a 1. So the relative maximum will occur at 1, 1. So we have 2 decreasing intervals, 1 increasing interval. We have a relative min at -3, -1/3, and a relative max at 1, 1.